Hello everyone. In the last video, we looked at logistic regression. We introduced the functional form for logistic regression, which is the logistic function or the logit function, or also known as the sigmoid function. In this video, we are going to look at how to learn the weights of this function. Remember that the logit function or the logistic function is parameterized using weights, and we are going to learn the weights using training data and use the learned weights to compute the predictions on test data. So the process of learning in logistic regression involves learning the parameters, which are nothing but the weights of the logistic function. So how to learn the weights is now an important question, right? So that's what we're going to address in this video. We are going to use a technique which we have introduced already in this course, which, if you remember, goes by the name MLE, or maximum likelihood estimation. We introduced this in point estimation. Here we are going to use MLE, we are going to change the function which we are going to maximize. So the function that we are going to use to compute the weights is a conditional log likelihood. Conditional log likelihood is given by this P of YL given XL. Now, we know that in logistic regression, we assume a functional form for P of Y given X. And when we calculate this quantity for training data that's already present, that we are going to use this data for training, right? It's already there and has labeled output class values. So we are going to take the training data, the features, and the corresponding true class label Y. And this is all part of training data itself. So that's why we have indexed them using L here, where L refers to the examples, the training data examples that are present. So each and every training data example will have a labeled Y value that is recorded and that is used for training. YL given XL. So we are going to use this function P of Y given X because that's what we know the form for in logistic regression. So the form for this P of Y given X is a logit function, right? And we're going to use that, and we're going to calculate W that maximizes this function, because this function here is parameterized by W. And the values of W that maximize this function are going to be returned as our learned values of W. So this is, after learning, we get this W. And at test time, we are going to substitute the learned values of W in our P of Y given X logit function. And that's our learned function, and use that function to predict the class values for test data. All right, so to learn the weights, we first take this function and then we expand it in this way to make it easier for us to learn the weights. So how do we do this? This function in interior part of this argmax is sigma over L, where L refers to the training examples, right? And YL is the prediction, is the output, the true label in the training example, and XL is the feature values of training examples. Okay, so to make our job easier, we are going to expand it in this form where we are going to say L of W. We are saying this entire thing is L of W, and then we expand that to be equal to sigma over L YL ln log to the base n P of YL is equal to 1 XL comma W plus 1 minus YL ln PL P of YL equal to 0 XL comma W. Intuitively, why are we doing this? We know that there are two different values of y. YL can take either value 1 or 0. And we know that the functional form for 1 is different from the functional form for 0, right? So if 0 is logit, this is 1 minus logit, right? We know that. And we can do this because if we have y values in 0 or 1, one of this is only valid each time we call out this example. Y is either 1 or 0, right? So let's just see for a specific example. Let's say y equal to 0. When y equal to 0, I'm going to expand this guy here, this whole L of W. Y equal to 0, then you have sigma over L. YL is 0. So this is 0 times something plus 1 minus YL, which is 0. So that becomes 1 because it's 0. ln P of YL equal to 0 given XL. So essentially, if y equal to 0, we don't need the YL equal to 1 term. So this term becomes 0 because this guy is 0. So let's now do it again for y equal to 1. For y equal to 1, we have sigma over L 1 times ln P of YL equal to 1 given XL comma W plus we have another term where y is equal to 1, so 1 minus 1, this becomes 0. This doesn't matter because this is 0, right? So now we know that y is equal to 1, and we can see that only the term where YL is equal to 1 is retained, the other term is just becomes 0. So we are just expanding it like in this fashion to cover both YL equal to 1 and YL equal to 0. So we can use the specific functional forms for YL equal to 1 and YL equal to 0 that we know and substituted it here whenever we get the corresponding value of y, just to make our computation easier. And we can see that it essentially only retains the right value of y, the term for the right value of y. Okay, now we have the expanded form. This expanded form is given here, the first line in the equation. Now we are going to make small adjustments to further simplify it and bring it in a form which is more easier for us to handle. Now we are going to combine these two guys here, this one, this term, and minus YL, this term. So we're going to expand it, these two, and we are going to, because they both have YL as the coefficient, we are going to bring them together, so to group them. So now we have YL, this goes in the numerator, this guy y equal to 1 goes in the numerator, it's coming from this guy, and we have minus YL here. So this guy, if you absorb it inside the log, it would go in the denominator. So we have YL equal to 1 in the numerator, probability of YL equal to 0 given XL in the denominator. And why we are doing this? Because we know that when we divide these two quantities, we already saw that it becomes simpler, right? We already said that that could be used for classification, and we would obviously like a simpler form, right? So that's why we are simplifying this further. Now we have this entire thing here. I'm going to erase some part of it just to make it clear. Okay, now we have this entire form here. We know already that the denominator, so I'm just going to work in the bottom where we have both these functional forms written. Y equal to 0 given x is the logit, and y equal to 1 given x is 1 minus logit, so we have an exponent in the numerator. Now if we evaluate this by this, right, this quantity by this, now this would go, we cancel, they're the same, and we will get this guy, just this part, right? This part is what we will get. And see that there is a log in front, so we'll essentially get ln of exponent w0 plus sigma I equal to 1 to n wi xi. This is what we will get. And now log and exponent, they cancel, so we essentially get this. So that's what we see here, right? That's the first term. Now the second term is this guy, this 1 times log. Now we have 1 times log YL equal to 0. So that is nothing but this guy, right? Now we can write this as, this is 1 by this, right? So we can, that's nothing but ln 1 by 1 plus e raised to w0 plus sigma I equal to 1 to n wi xi, right? Now we can write this as minus ln 1 plus e raised to w0 plus sigma I equal to 1 to n wi xi, right? So that's what we see here. We have a minus that's coming from here, and then we have this quantity here. Now we have simplified the form, and we have a functional form for the L of W, and we simplified it. The bad news is that there is no closed form solution to maximize L of W that we just simplified and created. We don't have a closed form solution to maximize L of W. But the good news is that L of W is a concave function in W, which means it looks something like the blue figure in the slides. There is no local minima, and there is one global minima. So because this function doesn't have many undulations, it has there is one true point which is the maximum, which is this point here, right? So this is the global maxima that we can find by incrementally searching for W. We search the space. This is a function in W, right? We solve this function, we keep searching, we if we reach a solution, that solution will be the globally optimal solution. But if our function, if our W, function in W, has this many peaks, it has only one peak here, right? It's clearly seen. If it has many peaks, then it would be hard for us to reach that point. That's what it means by, essentially, that's what it means by W, L of W being a concave function. Concave functions are easy to optimize using gradient ascent. So we are going to now learn an optimization technique called gradient ascent or gradient descent. Both are similar. Which direction that you search for W gives you a descent or an ascent. Essentially, both are used to solve this problem of finding the optimal value of W. And gradient ascent can be simplified and given in one equation as follows, where we have Wi is equal to Wi plus some value for learning rate times a partial derivative of Lw, the function that you're going to optimize, functional form of W. It's different from the logistic function. Remember that. L of W is what we derived for weights using the logistic function just now in this video before. So remember that it's different from the actual logit function that's used for classification. Often students confuse between these two functions. So this is a functional form that you're going to optimize to learn W, right? And you have a partial derivative of L of W with respect to Wi. So for each Wi, you can separately derive a partial derivative, and you can add that to the current value of Wi to search the Wi which is optimal. So for example, you start somewhere, let's say here, and then you continue to search. You keep moving where you have Wi plus some value. So maybe you move here next, and then you move here next, and so on, right? So that's how you keep traversing until finally you find this optimal value of Wi. Now we have L of W. We already simplified that. This is the simplified form that we have here. Now we want a partial derivative of L of W with respect to Wi. So we only care about the terms which have Wi, the ith weight. The rest of the terms are all constant when it comes to differentiation with respect to the ith weight. So we only care about the terms which have Wi. All other terms will be 0. So we have sigma over L xi of L. This is just the ith feature. YL minus probability of YL equal to 1 XL comma W. So this is coming from this guy. So you differentiate this with respect to Wi, you get this. So let's look at it a little more. Now, which term here has Wi? So this term does not have Wi, right? So this goes away. This term, there's one term here for the ith weight which has Wi. Rest of Wi minus 1, I plus 1, I plus 2, all those are zeros, right? So what is the coefficient of the term which has weight Wi? So when you differentiate with respect to that, only the coefficient remains. That coefficient is nothing but XIL, the ith feature value of the Lth example. So you still have the sigma over L, right? Because it's over L. And then you have YL, right? XIL, that's what is this term. So this first term, we understand where it comes from. It comes from differentiating this guy, right? Okay, now for the next term. So the next term we have minus log 1 plus exponent w0 plus sigma over I wi xil. Now when we differentiate log, it becomes 1 by 1 plus exponent w0 plus sigma over I to n wi xil, right? So this is what it becomes when you differentiate log. Now after you differentiate log, you are differentiating with respect to wi. So you also have to add the coefficient. The coefficient will also be multiplied to this. The coefficient of wi is nothing but xil. So that's why we have this quantity here. Okay, so now we understood what the exact derivation is, but we want to represent this in terms of functions that we already know. So now this guy here, this is nothing but your logit function. This is already, we know that. This is what we assumed is the form for P of yl equal to 1 given x, right? So we assumed y equal to 1 given x is this form. So that's what is here. That's what we have here. This guy, this entire guy is nothing but P of yl is equal to 1 given xl. That we are multiplying that by xil, and that is also there in this other term, the first term. So we can take that out as common. So that's here. So when we differentiate partially with respect to wi, this is what we get. This entire thing is what we get. So now gradient descent or ascent, whatever direction we are choosing to go, involves wi, setting wi to be wi plus eta, which is a small number that signifies how much you should move along the direction. When you differentiate something, and that would give you a direction to move. So this is the direction that you're moving in. And the amount you're moving would be given by this entire quantity. This is for just understanding more intuitively how this entire process is happening. So you have an initial weight, value, and you're updating the initial weight by adding a value to that. So you're sending in the direction that your algorithm is giving, the gradient ascent algorithm is giving you. In that direction, you are making a step. So this is one step. So we'll look at the algorithm, the gradient ascent, in more detail in the next video.